So now group 17, right? So group 17, group 2, we did group 2. So this is all group 17. So first thing, you got to remember the colors. The colors are that fluorine is a very pale yellow gas. It's a chlorine is a greenish yellow gas. थोड़ा बहुत आपको ना colors वगैरह. Fluorine is basically colorless, by the way. It's like even if you see it, I mean it's usually dilute. Hey, बहुत dilute होती है. I think this is very concentrated. That's a better version of how fluorine actually looks like. This one is, I think, very concentrated. Fluorine actually looks like this. Like it's almost colorless. Chlorine actually looks like this, greenish yellow. That's red brown, and then you've got iodine. That's blue black. That's purple. It's got a purple vapor. So starting with the first one, fluorine is very pale yellow. Almost colorless. Chlorine is greenish yellow. It's a gas. So that's a gas. Bromine is a red brown liquid, orange brown liquid. Iodine is a blue black solid. Normal iodine is it's crystalline, it's solid. Iodine has several colors. You can remember that. This is what iodine actually looks like in solid state. So this is what iodine looks like in solid state. It looks completely blue black. If you look at iodine in vapor form, so in vapor form it's purple. It's got a very purple vapor. Otherwise, in solid state, it's completely black. It's very blackish. And then iodine also dissolves in water. So iodine, if it's aqueous, it depends on the concentration. When iodine is aqueous, कौन सा वाला सही है? 1 second. I said it's 1 second. So iodine, when it's aqueous, it's this yellow brown solution. Okay, so remember, iodine has 3 colors mainly. In solid state, it's blue black. In vapor state, it's purple. और फिर ये solution के अंदर ना, it's going to be aqueous. It's going to be yellow or kind of dark brown, depending on how concentrated this is. तो ये सारे यहाँ पे लिखे हुए. It's yellow brown in aqueous solution, blue black solid, and purple vapor. Volatility decreases down the group. The melting points, boiling points increase. Why do they increase? Because they've got temporary dipole-induced dipole attraction, which means that they're completely non-polar molecules. So the electrons are kind of randomly fluctuating around. Sometimes this side becomes negative, sometimes this side becomes positive. And in the other one, the dipoles are also constantly switching around. The electrons are constantly shifting around. They're evenly distributed, but due to random collisions, the electrons at one time might be on this side, at another instant they might be on the other side. So there's going to be temporary dipole-induced dipoles or instantaneous dipoles. So the positive side will attract the negative side. Positive side of one molecule will attract the negative side of the other molecule, and that's van der Waals forces. The temporary dipole-induced dipole is basically van der Waals forces. Okay, so that is van der Waals attraction. And van der Waals attraction becomes stronger as you have more electrons. If you have more electrons, like iodine has 106 electrons. So if 106 electrons, they constantly switch around, that leads to a lot stronger dipoles. That leads to a lot stronger negative and positive charges, and that leads to a lot stronger attraction between molecules. So due to larger size, the temporary dipole-induced dipole attractions, they increase. And the colors, they also become darker. That's another trend. Okay. Ye sara clear? Is this clear?
Yes, sir.
Yes, sir.
अच्छा, अब उससे आगे ये कि we'll talk about bond strength. Bond strength is that how strong is the bond, and we are talking about the bonds in fluorine, chlorine, bromine, and iodine. Now the general rule is that smaller atoms have stronger bonds. Why do they have stronger bonds? Because the nucleuses are more exposed, they're less shielded. Like if you have a bigger atom, it's got so many electrons that it will not be that interested in some other atom's electrons. So, so a bigger atom with a lot of electrons will not attract electrons from other atoms because it's too shielded. So smaller atoms, they're less shielded. That will lead to more orbital overlap. That means they're going to attract each other much strongly. They're going to attract each other's electrons very strongly. And smaller atoms, they will be close together. So that's why if they've got a very short bond length because they're small, that also means there's going to be more attraction. Remember, attraction depends on the distance. So smaller atoms are close together. So normally what happens is that smaller atoms have stronger bonds. So bigger atoms have weaker bonds. So you can see iodine over here, it's got weak bonds. Bromine has slightly stronger bonds. Chlorine has even stronger bonds. The exception is fluorine. And why is fluorine an exception? This is the reason why fluorine is an exception. That that fluorine is such a small atom that the nucleus and the electrons they should be attracting each other very strongly. Like you've got these electrons in the middle that are being shared, and you got the two nuclei of the fluorine. There should be more attraction, but instead you actually have less attraction. And the reason for that is, and now this is an exception. Now the reason for that is that fluorine has so many these extra lone pairs, so many spare electrons, that when two fluorine atoms come together, there's a lot of repulsion between those electrons. So instead of the nucleuses getting attracted to the shared electrons, the shared electron attracting this nucleus, the shared electron attracting this nucleus. So instead of having a force of attraction, they actually have a force of repulsion, which is that these lone pairs, they start repelling each other. This lone pair will repel this lone pair, this lone pair will repel. So lone pair repulsion between fluorine atom weakens the bond. Is that clear?
Yes. Yes.
So just remember the first trend. Smaller atoms have stronger bonds, right? Except fluorine. That it's so small that the lone pairs, it would be very hard to keep those lone pairs together in a small atom. Now, when it comes to the bond strength of hydrogen halides, HF, HCl, HBr, HI, they follow the trend. There is no exception. The bigger atom has the weakest bond. The smaller atom has the strongest bond. So why is there no exception? The reason for that is, in this case, the reason for that is, okay, if you have, let's say, an HF molecule, then there is no lone pair repulsion because one of the atom doesn't even have lone pairs. I mean, this one has lone pairs. The fluorine atom has a lot of lone pairs, but the other atom doesn't even have lone pairs. So there's no repulsion. I mean, this thing has no extra electrons. So which is why that is not an issue over here. Is that clear? Okay,
Yes.
FF में issue है. HF का you don't really have an issue, right?
Hmm.
Right, is this clear?
Yes.
So then the next thing is they're going to talk about the boiling points of hydrogen halides. So the boiling points, remember, boiling points depend on not on the bond strength, they actually depend on the so they actually depend on so one thing I need to add about HI over here is that HI gets I guess not this part. One thing I'm going to add about HI, and that is let's add over here. Look, it's already, I think, added somewhere. Just a second. Probably this one. That HI has a very it's got a very weak bond. It decomposes even with a hot glass rod. You add a hot glass rod, it decomposes. It's got a very weak bond. So HI is going to form crystals of iodine as soon as you just put even without putting a hot glass rod, it's going to start decomposing. So just remember this thing, that pretty hard to decompose HF. It's got a very strong bond, but HI, that's kind of easy to decompose. Now coming back to the boiling points of hydrogen halides. Now remember, boiling points has nothing to do with bonds. It's more about intermolecular forces. So when it comes to boiling points, uh, this is what happens, that HF has hydrogen bonds, which is basically an extreme form of a dipole. Fluorine is one of the most electronegative atoms out there. So it's so electronegative that it has a very strong attraction for these shared electrons. So the negative charge that builds up on fluorine, that's very, very strong. And the positive charge that appears on hydrogen, that's also very strong. And another reason why HF has such a strong dipole is that the lone pairs over here, uh, they increase the negative charge, which is why this negative charge is not a small, slight negative charge. It's a pretty strong negative charge, which is why HF molecules, they attract each other very, very strongly. Is this clear?
Yes, sir.
Yes.
So remember, hydrogen bonds are extremely strong. So what about the other ones? So HF is going to have a very high boiling point. What about the other ones? The dipole, it decreases when you go down the group. You got a strong permanent dipole for HCl, but you've got a very weak permanent dipole for HI. The reason for that is that that the electronegativity decreases. Cl is less electronegative. Br is even less electronegative. Iodine is very less electronegative. So they're all, just a second. They, one second. So they're all going to have weaker attraction for electrons. The electronegativity decreases, which is why the strength of the dipole, it decreases, and you got a smaller positive, smaller negative charge, which is why the attraction between molecules is also going to be lesser. But what happens is that due to random collisions, the electrons are also fluctuating around, so they also have van der Waals forces. There's random fluctuation also happening. So bigger molecules always have more van der Waals forces. It's the random fluctuation. Like iodine over here has 53 plus 154 electrons. So these 54 electrons will be randomly moving around, right, during collisions. These 54 electrons in this molecule might go to one side during a collision, might go to the other side during a collision. So the temporary dipoles and the instantaneous dipoles that are being created, they're going to be relatively stronger in HI. Is that clear? You clear about?
Yes, sir.
Okay.
Yes.
So what happens is that what happens is that even though HI has a very weak permanent dipole, but it's got a pretty strong instantaneous dipole. Okay, let me. So then, is this dipole thing clear to you?
Yes, sir.
So, but I'm going to explain this anyways. It's you do remember electronegativity, right? That it decreases down the group, right?
Mm-hmm. Yes.
So you got a very small dipole in HI, right? But the thing is that this entire molecule has 53 electrons. Actually 54 electrons if you include hydrogen's electrons. Now, van der Waals forces is that these 54 electrons will be randomly just sort of shifting slightly to one side, shifting slightly to the other side. And that leads to the creation of these instantaneous dipoles. Maybe these 54 electrons very slightly shift to this side, the other side will become positively charged, right? Maybe in the next second, these 54 electrons, they shift to the right, this side will become negative and this side will become positive. So there's going to be random fluctuations happening, right? And that's van der Waals forces. So the permanent dipole is like very small, but the temporary dipole or instantaneous dipoles that are going to be created, they're going to be very large. Is that clear?
Okay.
So, so you got weak permanent dipoles. But you got very strong uh you got very strong instantaneous dipoles or temporary dipoles. So
So what do these two terms mean, sir?
which one?
The permanent and the instantaneous one, sir.
I think I'll just go over this very quickly. 1 second. I said, see if you have. Let me just go over. So let me go over this intermolecular forces very quickly. I say, you do understand this fact, right? That you've got a pure table. The elements on the right side and the elements to the top in this corner over here, they're extremely electronegative. Is that clear?
Yes.
That basically means that they really like to gain electrons. And there's a table. Let me open the table for you. Let me find this. Just 1 second. One table of electrons. So this table, just 1 second. So we've got this table of electronegativity values. They basically measure how strongly does an atom like to gain electrons. The numbers are written at the bottom. 4 is the most electronegative, that's fluorine. Then you've got oxygen, nitrogen. The electronegativity decreases, right? The elements that are in the corner over here, as you go down the group, the electronegativity decreases as well, right? Uh, and there are plenty of reasons for that. The reason why the right side elements are more electronegative is that they have more protons. Like if you go to the right, lithium has 3 protons. Fluorine, on the other end, has 9 protons. So 9 protons have a much stronger attraction for electrons because its nucleus has a positive 9 charge. Is that idea clear?
Yes, sir. Yes.
I said similarly, when you go down the group, the electronegativity or the tendency to attract electrons decreases. Because when you move down the group, the nucleus is already surrounded by so many electrons that it gets very, very shielded. Like it's surrounded by electrons. So it's already like this is what happens. Like iodine, if you look at iodine, it's got, I think it's got too many shells. It's got 5 shells, I guess, and it's got 53 electrons. So if there's 53 electrons, it would be very hard for iodine to attract another electron because all these electrons will be repelling that electron. So pretty hard. So you need to have a nucleus. Smaller atoms, they have a stronger attraction for electrons. Is that clear? Because they're less shielded. As anyways, so the idea is that uh, elements have certain electronegativity. If the difference is greater than, if the difference happens to be greater than 1.7, that means the compound is going to be ionic. Like if you take Na and you take Cl, what is the difference? Na is 0.9 and Cl is what? 3. So what happens is that one of the element is so electronegative that it's going to gain electrons from the other one. Is that clear? And it will become -1, and this one will become +1. Is that clear?
Yes.
Achha, but then you have covalent molecules. Covalent molecules are when the difference is less than 1.7. That means like in the case of uh, like in any case, for example, if you talk about any bond, for example, let's take a simple one. Let's say it's sulfur with chlorine, right? So sulfur is 2.5 and chlorine is 3. Now what will happen is that sulfur, the electrons are going to be shared, because although chlorine has a stronger attraction for electrons, but it will not be able to gain those electrons because the difference is not large enough, right? Is that clear?
Yes, sir.
I mean, it's like a tug of war. Like one of them is stronger, but not that strong. So the electrons will be slightly closer to the Cl, but so that will result in a polar bond. That's called a permanent dipole. Like the electrons are going to be slightly closer to Cl. Is that clear?
Yes.
Same is the case with HCl. If you look at HCl, it's going to be H is 2.1 and Cl over here is 3. So the electrons that are shared, they're just going to be very slightly closer to Cl. This will become slight negative and this one will become slight positive. So,
Yes.
so that's known as a permanent dipole. That means, uh, like if it was an isolated atom, right, that would mean that Cl will always be the negative side and the H will always be the positive side, right? And when you have this scenario, the molecules will attract each other. You're going to have an HCl molecule, you're going to have another HCl molecule. The H is always going to be positive, the Cl is always going to be negative, H is positive, Cl is negative, and they will attract each other. That's what is a permanent dipole attraction. That's an intermolecular force, TK. We did this in another chapter, we'll do that again, but later on. But you understand the concept of a permanent dipole.
Yes.
So, so the thing that we were doing over here, I explained to you that the permanent dipole attraction became weaker, right? Because that's how molecules are going to attract each other. HCl is going to have a stronger permanent dipole. HBI is going to have a weaker dipole. HI is going to have an even weaker permanent dipole. Is that clear?
Yes.
I said now, apart from permanent dipole, there's another thing as well, and that thing is known as van der Waals forces. Because these molecules are not isolated; they're actually interacting with their environment. They're bumping into other stuff, right? I mean, this is like a perfect HCl molecule in an isolated environment. This is how it's going to look like, right? Is that clear?
Yes, sir.
But this molecule is constantly bumping with other stuff, right? So it's got a total of I think 18 electrons. Cl is 17 and H is so that's 18 electrons, right? This also has 18 electrons. So in addition to permanent dipoles, it's also going to have temporary dipoles. Maybe for some random instance, these 18 electrons they slightly shift to one side. Maybe a collision happens and the electrons get knocked to one side. So if they get knocked to the left side over here, if they get knocked to the left side, then there's going to be a negative charge on this hydrogen, there's going to be a positive charge on this Cl. Is that clear?
Yes, sir.
So those are known as fluctuating dipoles. Next second, they might disappear. Maybe the electrons, they come back to their position, right? So it's not, so the temporary dipoles are not permanent. They're actually, they are in addition to the ones, in addition to permanent dipoles. Temporary dipoles are like fluctuations happening, right? And that's known as van der Waals forces, right? Is that clear?
Yes.
And van der Waals forces, this random fluctuation, maybe the electrons get knocked to one side, maybe the electrons get knocked to the other side. This van der Waals force is usually very weak, but it increases in size. If you have a bigger molecule, like this one has 54 electrons, right? The dipole is weak, like the permanent dipole is weak because iodine is not very electronegative. So same case over here, the other iodine. So the permanent dipole is kind of very weak. But imagine, imagine 54 electrons getting knocked to one side. That would result in a very strong temporary dipole. right? Is that clear?
Mm. Yes, sir.
So you got these two forces. You got van der Waals forces and you got permanent dipoles, right? Now, what's going on over here is that even though HCl has a stronger permanent dipole, but it's got very weak van der Waals forces, less van der Waals forces, because it's a very small molecule. So there are very few electrons. And even though HI has a weak permanent dipole, but it's got bigger or more stronger van der Waals forces because it's a bigger molecule. Is that idea clear?
Yes, sir.
So what is happening is that your graph over here, the HI has a stronger or a higher boiling point, and the reason is that it's got more van der Waals forces. Uh, Even though HCl has a stronger permanent dipole, HI has a weaker permanent dipole. But HI is going to have more van der Waals forces. That's why its melting point and boiling point will be higher compared to HCl. So they're going to ask you about this. So this is the explanation that you're going to write, that if even though the bond polarity and strength of permanent dipole decreases, electronegativity of halogen decreases down the group, but bigger molecules have more van der Waals forces, which increases down the group. Hence, boiling point increases. Is that clear?
Yes, sir.
Yes.
Okay. और जो first वाला है ना, that is known as hydrogen bonding. So the first one, HF, that's like an extreme version of a permanent dipole. Like, who's the most electronegative element in this periodic table? That's fluorine over here, right?
Mm-hmm.
So what happens is that since fluorine is one of the most electronegative, so fluorine will very strongly attract these electrons. So it's going to have a very big negative charge and a very big positive charge. It's going to have a very big permanent dipole. That's what you can say. Is that clear?
Yes.
But the negative charge is going to become greater as well because it's got these extra electrons as well that it's not using. So its outer shell is full of electrons. So that means the negative charge is even stronger, right? So what happens is that
Uh,
yeah,
sir,
yeah,
the difference between H and F is more than 1.7, right?
it's a lot more than 1.7.
So
Actually,
does
that's
it
it.
still go to it? Yeah, yes, sir.
Actually, you're talking about whether it's ionic or not. Um, this one is slightly because HF does ionize very quickly. So it's kind of this one is kind of in between ionic and covalent. Okay? But what I'm going to state about HF is that it's like right on the edge, it's right on the boundary. Um, and like, why were ionic compounds having high melting and boiling points? One second. So why were ionic compounds having high melting and boiling points? Because one of them had a very strong positive charge, the other one had a very strong negative charge, and then they all started attracting each other, right?
Mm-hmm.
So something similar happens in HF as well, except that it's not completely positive and the other one is not completely negative, right? Is that clear?
Okay, sir.
So which is why HF over here, let me where's the so over here you can see that HF is the one that's got this very very strong or very very high boiling point. Okay, is this clear?
Ji, sir.
Now the other thing is that I said no, I'm sorry. I said, but the whole explanation for this. Okay. I said, but the whole explanation for this. You're gonna be asked about this. Why is HF having such a high boiling point? Because it's got very strong hydrogen bonds. And why do HCl, HB, and HI the boiling points are low? Because they've got weak permanent dipoles, but the strength of van der Waals forces it increases down the group. So HI has relatively more electrons, so it's got more van der Waals forces. Is this clear?
Mm. Yes.
Ji, sir.
फिर नेक्स्ट है कि electronegativity, right? We just talked about it, that it decreases down the group, right? Iodine doesn't really like to gain electrons. Fluorine really likes to gain electrons. So what do you call something that likes to gain electrons? That likes to get reduced. That's an oxidizing agent, right? So down the group, they become weaker oxidizing agent. Fluorine really likes to gain electrons. Iodine does not like to gain electrons, which is why the common state of iodine is iodine. It doesn't like to gain electrons. It doesn't like to form I-1. Fluorine, on the other hand, is very reactive. It always likes to gain electrons. So you don't really see fluorine in the state of fluorine. It's always in the form of some negative ion. Is that clear?
Yes.
Same applies to chlorine as well. Like chlorine, you rarely see chlorine in the form of Cl2. What do you see it in the form of? I mean, in everyday stuff, you see it in the form of Cl minus 1, like in NaCl, right? Because it likes to gain electrons. Iodine doesn't like to gain electrons. So a lot of times the common state of iodine is I2, right? It doesn't like to gain electrons. Is this clear?
Yes, sir.
And the reason is smaller atoms are less shielded. They've got fewer shells, so they attract electrons very strongly. Now, the opposite is also true. That is that the negative ions, what about losing electrons? So now I'm talking about the reverse. Like the halides or the fluoride, chloride, bromide, iodide, what if they want to lose electrons? Now, the smaller atom will not like to lose electrons. F-1 does not like to lose electrons. It doesn't like to form F2. This is the reverse of the thing that we just discussed. Meanwhile, Br-1 and I-1, because they're bigger atoms, they really like to lose electrons. I mean, the nucleuses are too shielded that the outer electron is very far away. So they very easily lose electrons. And then and they form bromine and iodine. So bigger ions, they've got more shielding, so they lose electrons very, very easily. So they get easily oxidized, which is why these two are like really powerful oxidizing agents. Reducing agents, sorry. If they're getting oxidized, they're reducing agents. Is that clear?
Yes, sir.
Yes.
So now remember, this thing is very important that that when it comes to oxidizing ability, the fluorine and chlorine are really powerful oxidizing agents. The bottom two are like very poor oxide. They don't like to, they don't like to gain electrons. And when it comes to them acting as reducing agents, the bottom two are like really powerful reducing agents. The top two, they don't like to lose electrons. Now, there's a very typical reaction, which is, I mean, this reaction is about formation of hydrogen halides. They're like acids, HCl, HBr, HI, etc. These are like really common industrial acids. So how are they formed? So the first one, how do you form HCl? The way you form HCl is, and you have to remember this reaction, you add NaCl with H2SO4, concentrated H2SO4. NaCl is a normal table salt. And what happens is a displacement reaction happens where HCl gas gets produced. So this is what's happening. Then you take a beaker which has H2SO4. So the green particles are H2SO4. H plus 1 ions and SO4 minus 2 ions. And NaCl is also very soluble. So the Na plus 1 and Cl ions, they dissociate, right? Now what happens is that you've got a mixture of ions, sulfuric acid and NaCl all mixed together. But what will immediately happen is that the H plus 1 will attract the Cl minus 1 and they'll form HCl gas. So all the H plus 1 and Cl ions, they will start forming these fumes of HCl gas. And you get HCl gas in this way. Okay, that's why you get this misty white fumes of HCl. And what is left in the solution? That's NaHN SO4. So is this idea clear? Why is this a displacement reaction?
Yes, sir.
Yes.
Okay. So the other stuff that you get is NaHSO4, and you get white fumes. Now, I just told you that Cl ions, they don't like to lose electrons. Smaller atoms, they don't like to lose electrons. So, which is why it's a very bad reducing agent. You don't have a redox reaction. There's no redox reaction. It's just a simple displacement reaction. Now, what happens is down the group is when you do the same reaction for Br minus 1 and I minus 1, they become very good reducing. I just told you that bigger atoms, they really like to lose electrons. So, in this case, what happens is that you start getting a redox reaction. So when you try and react NaBr with H2SO4, what happens is you do get a displacement reaction. You get HBr in the same way, right? But eventually what happens is that I told you that Br minus 1 is a bigger atom. It likes to lose electrons. So Br minus 1, some of it might lose electrons to form Br2. And sulfur will gain electrons and its oxidation state will decrease from +6 to +4. So this reaction will also happen followed by oxidation because Br minus 1 is a pretty good reducing agent. Is that clear?
जी sir.
Yes.
So it's the exact same reaction, but there's an element of redox as well. You go further down the group, you get the same reaction with I minus 1 as well. Like just the same one with NaCl, you get the same reaction with NaI. But I minus 1 is an even better reducing agent. So what happens is that once HI is formed, I minus 1 is formed, I minus 1 very strongly starts to lose electrons because I told you I minus 1 does not want to form I minus 1. It loses electrons very easily to form iodine. So you get a lot of iodine getting produced and the sulfuric acid starts getting reduced. I minus 1 loses electrons, sulfur over here gains electrons. So you get some 2-3 types of reactions in which I minus 1 reduces the sulfuric acid to sulfur dioxide. Because it's a powerful reducing agent, it can reduce it to sulfur as well. It can also reduce it to sulfur with an oxidation state of -2 over here. so I minus 1 really likes to lose electrons. So sulfuric acid gets reduced to sulfur dioxide, H2S, or sulfur. And sulfur is, remember, yellow. H2S has a smell of rotten eggs. And iodine over here is purple. These are the observations that you're going to get. So the simple thing is, the first reaction does not have any displacement. Any redox reaction. Cl minus 1 doesn't like to lose electrons. So the only thing you get is HCl gas. The second reaction, same reaction, but Br minus 1 likes to lose electrons. So you get some redox as well. Third reaction with NaI, same reaction, but I minus 1 really likes to lose electrons. So you get a lot of redox reaction after that. So is this clear, this thing?
सर ये पहले जैसे कि NaBr plus H2SO4
हाँ
NaHSO4 plus HBr हो जाएगा सर यानी उसी वक्त में ही रिएक्शन हो जाएगा
हाँ
अगले वाला
हाँ
ओके सर
और मतलब ये भी हो सकता है, this Br minus 1 directly turning into Br2. जरूरी नहीं है कि स्टेप वाइज हो, ठीक है.
ओके सर
And but is this idea clear that the first one will have no redox reaction, and down the group the redox reaction will become more dominant? अच्छा, so
ओके सर वो सर यानी ये डिस्प्लेसमेंट फॉलोड बाय रिडॉक्स रिएक्शन कहते हैं
हाँ, अच्छा ये बस याद रखना है, ठीक है. They'll ask you a lot of questions about this. Okay, how do you form HCl? तो आप ये reaction बताओगे. How do you form HBr? What's the problem with forming HBr? Because you're going to get other stuff as well. How do you form HI? You're going to get very little HI actually. Most of it is going to get oxidized to form iodine. So the question now is, how do you prevent this redox reaction? Because remember, our purpose kya tha? Our purpose was, our purpose was for this reaction. The purpose was that we wanted to make HCl, HBr, and HI, right? we wanted to make this stuff, right? We actually did not want the redox reaction. So how do you prevent a redox reaction? The way you prevent a redox reaction is कि ठीक है भाई, Br minus one and I minus one are like really powerful reducing agents, but remember, जो ताली है ना वो दो हाथों से बचती है, which means that if one of them is a reducing agent, if one of them likes to lose electrons, the other one should like to gain electrons, right? That's how the reaction will happen. A redox reaction needs two things. It needs someone losing electrons, and it needs someone that's gaining electrons, right? Is that clear?
जी सर.
So you have a reducing agent, so the other one must be the oxidizing agent, that it must have some capacity to gain electrons. So sulfuric acid is a kind of a good oxidizing agent. It always likes to like gain electrons. So the way you can kill this redox reaction is that you replace the sulfuric acid with something that does not like to gain electrons. So the I minus one will not be able to lose electrons, because the I minus one is only able to lose electrons when the other one has the ability to gain electrons. So you can kill the redox part. So you can kill the redox part by Br minus one and I minus one will only give displacement reaction with H3PO4 instead of H2SO4, because H2SO4 was a pretty good oxidizing agent. H3PO4 is not an oxidizing agent. It has no ability to actually gain electrons. So in this case, you're not going to get a redox reaction. So you just have to replace the acid. Instead of sulfuric acid, you're going to use phosphoric acid. Is that clear?
जी सर.
अच्छा, इसके questions करेंगे वही होंगे ये, बस जल्दी से we'll finish this, ठीक है? This whole chapter, it's there's a disproportionation reaction, which is when an element gets oxidized and reduced at the same time. For example, Cl2 turning into Cl minus 1 NaCl. So you need to remember these two equations. With cold NaOH, chlorine dissolved in cold NaOH, it forms NaCl, NaClO plus H2O. Chlorine dissolved with hot NaOH, that's NaCl, NaClO3, and H2O. So you just have to remember this reaction. What happens with cold NaOH? What happens with hot NaOH? So then we did talk about the reactivity. I told you that fluorine was very reactive because it really likes to gain electrons. Iodine doesn't like to gain electrons. So the reaction becomes slower and slower when you go down the group. And we did talk about the stability of the bonds. HF was very strong. HI was a very weak bond. So thermal stability decreases. Bigger atoms, they always form weaker bonds. You need to know
सर.
the... हाँ जी.
सर ये H2 plus Br2 का सर ये वो इक्विलिब्रियम रिएक्शन क्या नहीं करता, यानी आयोडीन के साथ बनता है लेकिन उसके साथ नहीं
नहीं,
बनता.
वो HBr का bond strong होता है ना, so it doesn't really break easily. It doesn't go backwards. The HI bond is...
ओके.
HI bond जो था वो बहुत weak था ना, ये हमने यहाँ पे शो किया था कि कहाँ पे था HI.
जी सर.
HI bond जो था ना, उसकी जो bond energy थी, that was very weak. It was very easy to break the HI bond. So what happened was कि आपका जो HI है ना, वो जैसे ही बनता है ना, as soon as it is formed, it just breaks down again and it forms H2 and I2, right?
ओके सर. और सर ये थर्मल स्टेबिलिटी डिक्रीजेस का क्या मतलब है?
Thermal stability है कि how easily will the bond break. So the HF bond is going to be very strong. So it would be very hard for it to break. You would have to give it a lot of energy. HCl is very stable. HI is not stable. वो HI का मैंने example दिया था ना कि HI decomposes, बल्कि यहाँ पे लिखा हुआ है. I told you that HI decomposes even with a hot glass rod. It's just going to break down.
जी सर. ओके सर.
फिर ये O levels के test है of halides. So you add silver ions or silver nitrate followed by ammonia. So the white precipitate is formed with Cl. I mean, this is the reaction written as well. That silver ions with Cl ions, they form AgCl solid precipitate. Br minus 1 AgBr, AgI. Now, the first one is soluble in ammonia. So this is what happens. This is the equation. When you dissolve AgCl with ammonia, the Ag gets surrounded by ammonia molecules and it mixes with the water and Cl ions get produced. So the AgCl dissolves. And the second one, Br minus 1, it gets dissolved in concentrated ammonia. Or I minus 1 is not soluble. ये O levels के जो test है ना, if you remember them, exactly these. ठीक है, is this clear?
Okay.
और फिर ये कि
And
reactor
so we'll have to memorize the nitrate, carbonate, sulfate ones as well.
need the tests
Yes, sir. Yes.
for P3 they're actually given to you, but it's better to actually
Oh.
memorize them.
Okay.
वो यहाँ पे कहीं होगा, वैसे लिखा होगा इसके अंदर. ये अभी नजर नहीं आ रहा, लेकिन I'm pretty sure it must be somewhere. अच्छा, कहाँ गया हमारा ये group 17? ठीक है, right at the bottom. अच्छा, reactivity, as you know that it decreases down the group, right? So remember in O levels you had a reaction, more reactive displaces the less reactive. So if you react Cl2 with Ki, what happens? Cl is more reactive, right? So it's going to displace the iodide. Is this clear?
जी सर.
Yes.
सर ये सिल्वर क्लोराइड का किसके साथ रिएक्ट किया था?
मतलब ये वाला?
जी सर.
ये वो टेस्ट था ना जो O levels का. I gave the equations that when you add the test for ClI is that you add silver ions, AgCl white precipitate is formed, which is soluble in excess ammonia. When you dissolve it in ammonia, you get this thing in the solution.
तो सर बाकी दो का ये नहीं होगा ना?
But reaction यही होगा, लेकिन the solubility decreases. Like for iodide, it's not soluble in ammonia. AgI will not dissolve in ammonia. Is that clear?
जी सर. तो सिल्वर क्लोराइड और सिल्वर ब्रोमाइड की होगा सर.
हाँ, लेकिन bromide भी only when it's concentrated ammonia.
ओके सर, ठीक.
अच्छा, बाकी फिर ये बस खत्म हो गया. Uses of halogens, you use it in swimming pools to kill bacteria. It's a disinfectant. Okay, when it mixes with water, it forms two acids, chloric 1 and hydrochloric acid. It's a bleaching agent, NaClO, that also kills bacteria as well. CFCs, chlorofluorocarbons, okay, these are inert, volatile solvents, aerosols, etc., which cause ozone depletion as well. They're used as refrigerants. तो ये सारा आगे जाके organic में भी पढ़ेंगे. But these are some of the common uses. Bromine compounds are frequently used as fire retardants. ठीक है, मतलब fire retardants का अगर formula देखोगे ना, fire retardants, most of them are kind of bromine compounds. ठीक है, यहाँ पे अगर किसी का formula दिया हुआ है, 1 second. मतलब for example ये, अच्छा formula किसी का भी दिया हुआ, sorry, 1 second. ठीक है, I guess this one. I mean, this is what a fire retardant molecule looks like. It's so a lot of bromine compounds, all of them, these are fire retardants. ठीक है, so they act as very good fire retardants. ठीक है, ये भी थोड़ा सा याद रखना है. Where's the board? Bromine compounds are very good fire retardants. Is that clear?
जी सर.
चलो ठीक है, कल फिर इसके वो करते हैं, क्वेश्चंस वगैरह करते हैं. ठीक है,
ओके सर.
Okay, sir.
चले, ओके, ठीक है, अल्लाह हाफिज.
अल्लाह हाफिज.
Thank you, sir. Oh, sir, tomorrow do we have class, sir?
We're going to have class tomorrow. ठीक है,
Same time, right?
हाँ.
Okay.
ओके, अल्लाह हाफिज.